Today we're going to talk about pressure sensor application in EV traction battery for detecting lithium-ion thermal runaway process. Let's look at pressure change in lithium-ion battery thermal runaway. As you can see, as one cell goes into thermal runaway, gases are produced due to chemical reaction, due to which the internal pressure builds up and the cell encapsulation is ruptured. Then cell beginning to vent and eject hot gases. And also the adjacent cells also starts to go into thermal runaway process. And again, more additional gases are produced. And within minutes, the battery housing is damaged and the battery starts to vent gases. Let's investigate the thermal runaway process in detail. The causes of cell encapsulation being ruptured can be a vehicle fault, crash, charger fault, or internal cell fault. As you can see, the cell ruptures, the heat and gases are produced, and it gives an opportunity to check for pressure rise measurement. Also, as one cell goes into thermal runaway process, the reaction travels to the other cell as well as the whole battery pack. And within minutes, the whole battery pack is destroyed. So if you consider at constant temperature, as the cell ruptures, the volume decreases. Hence the pressure should rise to compensate for the lost volume. This is according to the ideal gas law. Here's a figure showing comparison of various sensors for detecting lithium-ion thermal runaway process by a study carried out by University of Stuttgart, Daimler, and Accumulative. As you can see from the figure, the visible venting coincides with the pressure spike. Also, you can see in the purple line, the gas sensor provides a signal way before the venting has happened. But the gas sensor has following implementation issues: selectivity. So the output of the gas sensor may be confounded by the pollution inside your battery pack. So it can provide you a false alarm. Second, the power consumption of the gas sensor is way more than the pressure sensor and the temperature sensor. Also, different cell chemistry will require different gas sensors to detect the lithium-ion thermal runaway process. Similarly, the temperature sensor, as you can see from the black dotted line, is very too slow to react to the venting procedure. Therefore, because of the implementation issue of the gas sensor and the temperature sensor being slow to react to the venting of the battery pack, the pressure sensor seems to be the most viable and the quicker solution to detect lithium-ion thermal runaway process.
Now let's look at the battery pressure monitoring product strategy. The current solution consists of FXPS device, which is available in 250 kPa and 165 kPa pressure ranges. This device is already in production. It is a standard device with no low power mode. It does have an SPI I2C or analog output interface. It needs a host MCU to read out the pressure, and it is available in QFN 4x4 package. Another series for battery pressure monitoring device is the NBP8X, which will be released to production in mid-2021. It does have an integrated MCU, an internal oscillator. It enables the wake up of the host MCU on a pressure change detection, which we'll be seeing in the next slide in detail. It is available in low power mode, and it has 70 microamperes average power consumption at 70 millisecond sampling interval. It has pressure, temperature, measurement capabilities. It does contains an NXP firmware tailored towards the application need. It is also available in QFN 4x4 package. So the main differences between the two devices is the low power consumption and the ease of use. If you have limited number of IOs in your MCUs, then you can always go for an FXPS device, which consists of I2C or analog output interface. But if you want a more smarter solution, low power mode, and the ability to wake up and host MCU, then the BPMS device, which is NBP8X, is perfect for your application.
Let's look into the FXPS series in detail. If you look at the block diagram, the pressure change is detected by a pressure transducer and the signal is converted by a C to V converter. Then the noise is removed with anti-aliasing filter and is converted to a digital signal by an A to D converter. Let's look at the key attributes for FXPS series here. It is available in 165 or 250 kPa pressure ranges. It is qualified according to AEC-Q 100. The temperature range is from -40 to 130 degrees C. It is an excellent accuracy of ±1% between 0 degrees C and 85 degrees C temperature range. It is available in SPI, I2C, or analog interface. It also has a small package of QFN 4x4. The pressure sensor is also protected by a chemical resistant gel. Has an internal self-test for a transducer and a signal chain. Here are the recommended part numbers with their interfaces and the pressure ranges. Now let's look at the new and the upcoming pressure sensor family for battery pressure monitoring sensor. The NBP8 device can detect the pressure change and send alarm to the host MCU based on the following event: reach absolute pressure threshold, reach relative pressure threshold, reach rate of change of pressure threshold. Here are the main parameters of the NBP8 device. The pressure range is from 40 to 250 kPa. The typical sensitivity is 0.2 kPa per LSP. The average current is 70 microamperes at 25 degrees C at 3.3 VDD at 70 millisecond sampling time interval. The standby current is 180 nanoamperes. The supply voltage is from 2.1 to 3.3 volts. It is available in SPI and PWM interface. Some of the features are an internal timer to periodically measure and compensate pressure, saves 12 recent measurements in memory. It has diagnostic on pressure transducer and internal connection. It has an embedded MCU to allow for function customization. It is qualified according to AEC-Q 100 and the temperature range is from -40 to 125 degrees C. Here are the part numbers and the pressure ranges associated with it. And as you can see that this pressure sensor will be releasing in mid 2021. Here's an example of a EV battery pack design example. The pressure sensor is located in the BMS controller, which manages the battery systems. Here are the typical requirements for the application, which we gathered from talking to dozens of OEMs and tier 1s. So the pressure range is from 40 to 250 kPa. The temperature range is -40 to 125 degrees C. The operating supply voltage is from 3.3 to 5 volts. Low power mode is very critical. Then wake up on pressure change, that seems to be a very important criteria as well. The interfaces are SPI, I2C, analog, and in some special cases, PWM. Here are the recommended part numbers like NBP8F DT4, which is a SPI version, the NBP9F D4T1, which is PWM and a SPI version, the FXPS 72 analog series, and the FXPS 7250 digital series. Similarly, here's another example of energy storage system containing lithium-ion battery pack. So the typical application requirements remains more or less similar to the battery pack inside the EV vehicles. The only difference is like this large containers contains several hundred battery packs. So if a battery pack contains one pressure sensors, so this large containers can contain like hundreds of pressure sensor, and the recommended part numbers remains the same, and the typical application use case remains the same in this kind of systems as well. Just to give you a little more insight into the battery monitoring system, here's a reference design of an EV vehicle. The pressure sensor is located inside the battery monitoring unit, and the details of the battery monitor unit is on the next slide. As you can see, the pressure sensor communicates with the main MCU, and in turn the main MCU alerts the driver to get out of the car before the thermal runaway process happens. Here's another example for the reference design for integrating the pressure sensor with the BMU controller S32K344. The pressure sensor can be an FXPS analog version if there are limited number of IOs. Otherwise, it can be FXPS digital pressure sensor, or it can be an NBP8 FD device as well. Here's the evaluation for NBP8 device. The NBP8 shield board is plugged into the Freedom KW36 board, which is connected to a computer running the NXP sensor GUI. The Freedom board is programmed with the demo project Freedom KW36A project for NBP8. The demo package is available on the link shown here after registration on NXP website.